There are a lot of disorders out there that can involve hemoglobin, a protein that is found in red blood cells. These disorders often cause similar symptoms in people. So what can we do to help to distinguish one from another? In this video, we are going to be looking at hemoglobin electrophoresis, what it is, how it works, and how it compares to something called an HPLC test. Hemoglobin electrophoresis is a test that can be ordered by health professionals to determine the types of hemoglobin that are present in someone's red blood cells. As the name might suggest, the test uses technology behind gel electrophoresis to separate out the different hemoglobin variants in a sample. First, the blood sample undergoes preparation so that the red blood cells are pre-lysed or pre-broken. This sample now contains free-floating intracellular contents from the red blood cells, and we call this type of sample hemolysate. Small amounts of hemolysate is then loaded into a well on a block of gel medium that sort of has the consistency of firm jello. This gel is used because its molecular structure creates a kind of matrix, or netting, that is able to act as obstacles and slow down molecules that are going through it. The gel is then placed in a tray with a buffer liquid, where an electric current will pass through the gel. One end of the tray, where the wells are, is negatively charged. The other end is positively charged. The hemoglobins themselves usually carry a net charge too, depending on the pH of their surrounding environment, and also of the amino acids that make up the protein. In the bloodstream, where pH is slightly basic at around 7.4, hemoglobins generally carry a negative charge. Because of this, buffers used in hemoglobin electrophoresis are generally alkaline, so that with time, the negatively charged hemoglobins will be attracted to the positive end of the gel and slowly migrate away from the origin well. Different variants of hemoglobin are made up of different globin chains with different amino acid compositions. This results in differences in net charge for each type of hemoglobin, which then leads to variation in the distance that hemoglobin migrates away from origin. For example, adult hemoglobin is made up of 2 alpha chains and 2 beta chains, while fetal hemoglobin is made up of 2 alpha chains and 2 gamma chains. Although they have alpha chains in common, the difference in amino acid composition between beta and gamma chains causes adult hemoglobin to migrate further on the gel than fetal hemoglobin. By studying the mobility of different hemoglobin variants, we can then make note of the approximate distances that each hemoglobin variant will travel. This information can then be used to figure out which variants are present in a sample. Now let's take a look at how this might be useful. A physician orders some blood work for a 31-year-old patient with mild anemia. Their complete blood count was normal, with a normal number of red blood cells. Although the patient had a slightly lower number of hemoglobins than average, these are their hemoglobin electrophoresis results. As you can see, there are 3 bands on the gel. The first band corresponds to adult hemoglobin, the second band corresponds to fetal hemoglobin, the third band can correspond to a number of different types of hemoglobin, including hemoglobin A2. The first and third band make sense, but the second band is unexpected for the patient's age. Production of fetal hemoglobin should have been mostly stopped by 1 year of age. This result suggests to us that this patient may have beta thalassemia, but we need some more information on exactly how much each hemoglobin variant is present. This is where HPLC comes in handy. HPLC stands for High Performance Liquid Chromatography, and it allows for the quantification of molecules in a sample. The basic laboratory technique in use here is chromatography, which is best exemplified in a classic experiment that many of you may have done in the past. You draw a dot on a piece of filter paper with a marker, then partially submerge the paper in water. Over time, the water moves up the paper, taking the dot along with it, and you can watch the marker ink slowly separating into its component dyes. Now we're going to take this process and add to it. HPLC is usually done in a large machine with several parts. It starts with what's called a mobile phase, which is a liquid solvent whose main job is to move the sample along the system. Water was essentially the mobile phase in our previous example. In this specific case of measuring hemoglobins, though, there is a little more to the mobile phase, because in addition to moving the sample along, it also partially helps to separate out the different hemoglobin variants. More on this later. This solvent then goes through a pump to help move it along at a steady and constant flow. As the solvent leaves this pump, the sample of hemolysate is then introduced to the mobile phase. Together, they encounter the stationary phase, whose main job is to separate out the different molecules in the sample. In our previous example, the filter paper acted as the stationary phase, but for hematology purposes, this is usually a cartridge of silica gel. This silica gel is negatively charged, which causes the binding of various hemoglobin types based on the number of positive charges that they have on their amino acid chains. The mobile phase starts to remove the least positively charged hemoglobins from the cartridge first. The machine can then up the ionic strength, or the concentration of ions, in the mobile phase, so that even the more positively charged hemoglobins are ripped off of the silica gel. This increase in ionic strength continues until all hemoglobins are persuaded to let go of the stationary phase and be moved along by the mobile phase. Once the hemoglobin variants eventually leave the cartridge, they are carried along to a detector, which eventually provides a quantification of the hemoglobins. As the hemoglobin variants were previously separated by charge, the variants enter the detector at different times, one after another, causing peaks in the amount of hemoglobin passing through the detector. By studying approximately when a hemoglobin variant usually enters the detector, we will be able to tell which peak corresponds to which hemoglobin variant. Going back to the patient, their doctor orders an HPLC to be run on their blood sample, and the report returns like this. By looking at these peaks, we have confirmed that they have fetal hemoglobin, adult hemoglobin, and hemoglobin A2 present in their red blood cells. But now we also know that fetal hemoglobin is actually the most prominent type of hemoglobin in their red blood cells, as opposed to adult hemoglobin. We also see that their hemoglobin A2 levels are slightly higher than normal. This result strongly suggests that the patient may have a form of beta thalassemia due to the significantly reduced levels of adult hemoglobin and increased levels of hemoglobin A2. The higher levels of hemoglobin A2 is indicative of excess alpha globin chains pairing with delta globin chains when there aren't enough beta globin chains around. The patient's high levels of fetal hemoglobin and their less severe symptoms also suggest that this patient may have hereditary persistence of fetal hemoglobin. This actually works in the patient's favor, as the continued production of gamma chains means that they will continue to pair up with alpha chains, preventing excess alpha globin chains from forming abnormal hemoglobin variants that don't transport oxygen efficiently.